Good afternoon. I'm Dr. Kanade. Today we will continue our discussion about the uh, call and return instructions. In particular, yesterday we have seen one example of how a program can utilize a subroutine which enables us to use a certain code to run multiple number of times and at different locations in the main program. Concretely, what we have seen yesterday was this program, right? We uh, we discussed the program of toggling all 8 bits of port B. At one instance, we sent 55H, and then we provided certain amount of delay, and then we sent double A, and then again we provided certain amount of delay. Okay, because we needed this delay at these two locations, that's why what we used a subroutine called delay, which we had written separately. And because of this arrangement of subroutine, what we can do is we can call the same code at different locations in the main program. At different locations means at different after different uh, instructions, or in different scenarios you can call that program. Let's say at certain in the same program, let's say you wanted to insert the delay twice, let's say here once and at this location twice, so you could have called the delay again. That is also possible, right? So this is the main advantage of having the facility of writing subroutines. Secondly, the difference between subroutine and loop. Can somebody guess what is the difference? In loop also we are using the same sequence of instructions or the same set of instructions multiple number of times. We are repeating the same instructions n number of times in loops also. But it is not the same as subroutine, right? Because suppose I write one code and one loop here at this location. Okay. But I suddenly want the same code at some other locations, let's say starting from here onwards. I want the same thing to happen again. Loops cannot do that. Loops are placed at one location and they will be executed at the same location itself only. However, when we write subroutines, this subroutine when we write once, we can use them multiple number of times. That's why I have used this program to illustrate that we can use the same subroutine multiple number of times, and that too at different locations. Now, in order to make it a little bit more clear, and in addition to our discussion about the call and return instructions, I'm going to show you something on the next slide. How call and return instructions are working when we are using the subroutines. We will see here. Okay, suppose let's see this is our main program. Okay, means the one that we were talking about in the last example. If you see, this main program was the program where we had written the 55 AA port B and those kind of instructions. Now let's say you want to call a particular subroutine, let's say at this particular instance. So what is happening? What makes the subroutine work, or what makes the automatic returning, coming back, going to the subroutine, coming back to the main program, how does it exactly work? Actually, we have already discussed this at the time of discussion of call and subroutine instructions, but since now we have already seen one example, to make it a complete loop, I'm talking about this now. Okay, so when we come across one particular call instruction, let's say at this particular instance, let's assume that the address of this instruction is X. Okay, the address of this particular instruction is X. The address, which is this address? This is the ROM, right? Program memory we are talking about. We are not talking about the RAM. We are not talking about the data memory. That access bank 0 to 15, that thing is different. That is about data memory, RAM. Here we are talking about the program memory. We have written instructions in the main program, and let's say call instruction is written at address X. Now, if you can recall, call instruction is a 4-byte instruction, right? That's why this instruction, the next instruction to call, the address is X plus 4. Okay, clear? Now, when this call instruction is getting executed, what will happen? First thing, the stack pointer will increment. You see here, stack pointer STKPTR means stack pointer is equal to stack pointer plus 1. Means whatever the value of the stack pointer was initially, that will first increment. Okay, note down the sequence of operation also. Stack pointer will increment first. Okay, as the definition tells, stack pointer always points to the top of the stack. Means now we have top of the stack updated. At that top of the stack, TOS means top of stack. Okay, at that TOS we write the address X plus 4. What is this address X plus 4? This is the address of the next instruction to the call. Okay, address of the instruction which is next to the call in the main program. Okay, in the calling program. So this X plus 4 goes to stack, and now PC means what? Program counter is loaded with value M. What is this M? You see here, M is the address of sub 1, address of the subroutine 1. We are calling subroutine 1 here, right? So when we are calling the subroutine 1, what happens first? Stack pointer gets incremented, then the address of the instruction which is written next to the call is loaded into the stack using this, and then program counter is loaded with M. Okay, this M is in this case address of the subroutine, address of the first instruction of the subroutine. Now this is all happening at what time? All this whole thing is happening when? During the execution of the call instruction, right? So at the time of call instruction itself, PC gets updated with M. So what will be the next instruction to get executed? The microcontroller executes instruction at address given in PC. As usual, PC always holds the address of the next instruction to be executed. Now the contents of PC is M, means this. So instruction, whatever instruction is written here, that will be executed next. Means after call, this particular instruction will be executed. Okay, means what? When we call a subroutine, the program control will go automatically to the subroutine. Instructions in the subroutine will be executed one by one as the sequence goes on, and at the end of the subroutine we must have this return instruction. Now what this return instruction is going to do? When the return instruction comes, whatever process we have written here, a reverse of that process happens. Means what? The PC means program counter is loaded with the contents of TOS. Means what? This value X plus 4 will come back to PC, and STKPTR means stack pointer will be reduced or decremented. So what will happen? PC now contains TOS, means PC contains X plus 4. So this X plus 4 is now loaded into PC, and then stack pointer is also automatically reduced. So after executing the return instruction, the next instruction that will be executed will be this one, because PC now holds x plus 4. Are you getting this? Is it clear now? See the sequence of events. When we are calling first stack pointer increments, the address of the original next instruction goes to top of stack. The address of instruction to be executed, means the subroutine, address of the subroutine gets copied to PC. Then the subroutine gets executed, and when we call the return instruction, the top of stack value goes back to PC. So the original next instruction address now goes back to PC, and then stack pointer is decremented. And because of the PC contents now TOS, means x plus 4, this instruction will be executed, right? So call, then subroutine, and then coming back to the original locations. Is it clear until this point? Anyone has any questions? Any questions? No question? Okay. So as seen in the yesterday's program, the same subroutine can be called multiple number of times. For example, here in the main program, again, let's say we have at address y, we have call sub1, the same subroutine we are calling again. So what will happen here? The control will again automatically go to sub1, and during this transfer, means during this call sub1, the second call, stack pointer will again increment, TOS will again be changed, but at this time what value will go to TOS? TOS will be equal to what? Y plus 4 at this time, because this is the address of the next instruction. So y plus 4 will now go to TOS, and PC, what will be the contents of PC? It will be again, PC will be equal to M, because we are calling the same subroutine. We are calling sub1 again. Okay, sub1's address is M. So after executing this call instruction at this location, TOS will be y plus 4, but PC will be still M. Again, when we come back, we'll come back to the next instruction, because during the return, PC will become TOS, and TOS in this case was how much? TOS in this case was y plus 4. That's why PC will have y plus 4, and that's why this instruction will get executed next. Okay. So from this diagram, you can see that we can call the same subroutine multiple number of times from the main program, right? We can have multiple subroutines return, okay, like this. We can have multiple subroutines, subroutine 1, subroutine 2, we can go on and on like this, and we can call them. Let's say here we are calling sub2, so the control will go to sub2, and when we write a return instruction in that sub2, we'll come back to the next instruction again of this call. This automatic returning is very important to understand, and that is happening because of this particular operations, the stack pointer. This thing is very important for the functioning of the stack, for the functioning of the automatic returning of the subroutine. Okay.
सर
Yeah.
सर आपण पीसी मध्ये जो ऍड्रेस असेल किंवा हे सबरूटीन मध्ये डिलेपलो जो आपण ऍड्रेस देतो सर, तो रॅम मधला ऍड्रेस दिलेला असणार ना आपण?
रॅम नाही, रोम मधला प्रोग्राम मेमरीतला,
प्रोग्राम मेमरी मधला ऍड्रेस दिलेला असेल का? आणि आपण मूव्ह WF ते इन्स्ट्रक्शन यूज करतो, त्याच्या पुढे ऍड्रेस तो रॅम मधला असेल?
तो रॅम मधला असतो. सी, आपण जेव्हा डेटा सोबत खेळतोय, डेटा आपण जेव्हा मूव्ह म्हणत होतो तेव्हा आपण डेटा मूव्ह करत होतो किंवा ऍड म्हणत होतो तेव्हा डेटा ऍड करत होतो. दॅट डेटा इज स्टोर्ड इन रॅम. ओके, डेटा जो आहे तो रॅम म्हणून त्याला आपण डेटा मेमरी म्हणतो. हा डेटा आहे का? हे काय आहेत? इन्स्ट्रक्शन्स. इथं परत काहीतरी मूव्ह ऍड असला काहीतरी इन्स्ट्रक्शन असतील इथं काही.
आणि सर मग जे मूव्ह ऍड इन्स्ट्रक्शन असेल त्याच्या पुढचा जो आपण ऍड्रेस लिहिला असेल तो रॅम मधला असेल ना?
हा, मूव्हच्या पुढचा जो ऍड्रेस असतो तो रॅम मधला असतो, पण मूव्ह इटसेल्फ कुठं लिहिलेली असणार आहे?
रोम मध्ये.
ती रोम मध्ये. कारण मूव्ह आपण इन्स्ट्रक्शन ज्या लिहू त्या रोम मध्ये लिहू आणि इन्स्ट्रक्शनला जो डेटा प्रोव्हाइड करतोय तो डेटा रॅम मधला असणार आहे. येते लक्षात? दोन गोष्टी वेगवेगळ्या आहेत बघा. एक म्हणजे इन्स्ट्रक्शन आपल्याला कुठेतरी लिहावे लागतील मायक्रो कंट्रोलर मध्ये, त्या इन्स्ट्रक्शन लिहिल्या जातील रोम मध्ये. ओके, आता या मेन प्रोग्रामच्या असोत की या सबरुटीनच्या असोत, हे इन्स्ट्रक्शन्सच आहेत, म्हणजे बेसिकली तो प्रोग्रामच आहे. सो प्रोग्राम इटसेल्फ विल बी रिटन इन रोम. सो हे जे ऍड्रेसेस आपण बोलतोय एक्स वाय, y+4, x+4, m, हे सगळे ऍड्रेसेस आहेत रोमचे. ओके, आणि या मूव्ह किंवा ऍड या इन्स्ट्रक्शन, हे मागच्या स्लाइडवर बघा, त्या मागच्या प्रोग्राम मध्ये हे जे दिसतात आपल्याला, हा आता LW आहे समजा, याला ऍड्रेस नाही आहे. लेट्स से आता इथं हा पोर्ट बी या ठिकाणी आपण ऍज अ एफ आहे, म्हणजे एक रेजिस्टर आहे, राईट? पोर्ट बीचा SFR आहे पोर्ट बी हा, राईट? हा कुठं आहे? तर हा एफ म्हणजेच कुठं? तर डेटा मेमरी मधला आहे. हा जो म्हणजे इन्स्ट्रक्शनच्या मध्ये जो दिलेला ऍड्रेस आहे, हे सगळे हे जे खालचे ऍड्रेसेस दिसतात, एक जर व्हॅल्यू असेल तर तिला काही ऍड्रेस नाही आहे, बट इफ इट इज SFRs or any F, then that F is from RAM. Okay, this F is from RAM. Like this my REG आपण एका रॅम लोकेशनला असाइन करत असतो, कारण F is always part of RAM. Okay, but here at this time we are not talking about the data being processed. What we are talking about? We are talking about the program flow. Okay, आता याच्यात थोडस तुम्हाला कन्फ्युजिंग अशामुळे होऊ शकतं की तुम्ही जर 8051च्या कॉल आणि रिटर्न सोबत जर का तुम्ही कम्पेअर करत असाल तर त्याच्यात एकच मेमरी होती, बरोबर आहे? 8051 मध्ये एकच मेमरी होती, ज्याला आपण सेपरेटली एक लोकेशनला आपण स्टॅक डिफाईन करायचो आणि मग त्याच मेमरीत आपण प्रोग्राम पण लिहायचो, डेटा पण वापरायचो, त्याच्यासाठी सगळं एकच होतं. दॅट्स वाय देर कॅन बी अ कन्फ्युजन. But here in PIC18F458 we have actually two memories, which is one is for manipulating data, जी आपण data RAM memory म्हणतो, and the second memory is program memory or ROM, where we write our programs. आणि याच्या व्यतिरिक्त एक सेपरेट सेक्शन आहे जो आहे स्टॅकचा, which is not even part of program memory or data memory. Our stack is separate, right? That we had talked about earlier कि स्टॅक मेमरी ही सेपरेटली अवेलेबल मेमरी आहे, ज्याच्याने ह्या मेमरी सेपरेट असल्यामुळे काय होतं की आपला मल्टिप्लेक्सिंगचा आणि आपला डेटा ट्रान्सफरचा टाइम वाचत असतो या कॉम्प्युटरमध्ये, या मायक्रो कंट्रोलरमध्ये. If you can recall, we have seen that there are separate two memories, and this is the characteristic of Harvard architecture, right? In von Neumann architecture, which was followed in the 8051, there was single memory. Here in PIC18F we have two separate memories. This is following the Harvard architecture. Okay, whenever we are talking about the addresses, okay, आता हे जे आपण बोलतोय हे ऍड्रेसेस बद्दलचं, हे ऍड्रेसेस आहेत रोमचे, आणि सेम काइंड ऑफ डिस्कशन इज ऍप्लिकेबल फॉर go to instructions, branching instructions, conditional branching instructions also. ओके, म्हणजे हा जो नेक्स्ट ऍड्रेस आहे, आता डिफरन्स काय आहे कॉल आणि गो टू मधला, की जेव्हा गो टू इन्स्ट्रक्शन येते, I will just instead of this call, let's say there was go to here. Okay, go to sub1. If I write the instruction like this, go to sub1. Okay, what will happen is only this thing will happen. I have rounded in blue. Okay, go to sub1. जर का instruction असेल तर only PC equal to M will happen. This stack pointer and TOS will not happen, will not take place. Means what? If go to sub1 is executed, the program will go to sub1. Okay. Technically, there is nothing right like subroutine or a label or anything like that. Technically, sub1 is just a label given at this particular location. Okay. So go to sub1 is also possible, but in that case, the program from here will go directly to sub1 and then execute these instructions. But it does not know how to come back to the original location, because this stack pointer and TOS and writing to the stack does not take place in goto. In that case, if you write return, then you will get into a bug, because it will return instruction is going to perform this task, and if you have not written anything on the top of stack or anything is not gone to the stack, it will take some random value whatever it was on the previous stack and go to that particular location. So that's how you can fall into errors. That's why I was telling in the previous lecture also that return instruction should not be used independently. It has to be followed in a combination of call and return. म्हणजे आपण जर कॉल केलं एखाद्या सबरूटीनला आणि तिथून रिटर्न येत असलो तरच ते ऍप्लिकेबल ठरेल. ओके, this particular section STK-PTR and TOS, this is actually useful for coming back to the original location. Okay, this address on this side written here, address M, this is also part of the ROM. Okay, this address is also part of ROM only. Okay, this is not part of RAM. Whatever we are writing, even this subroutine 2, this is also written in the program ROM only. Note that all the instructions, whatever instructions we are writing, all the instructions go in the program memory only. Okay, and manipulation of data, calculations on the on any values, reading any values, writing any values, that happens in the data memory called RAM. That is separate memory. Okay, is it clear until this point? Any other questions? Okay, now in this case what we have seen that on this slide what you are seeing is there are two subroutines, sub1 and sub2. We are calling these subroutines from the main program. Means from here we have called subroutine 1 at once, then again we call the same subroutine, and at this location we have called the subroutine 2. Okay, so it is coming back to this. So this is one simple arrangement you can say, but it is also possible to call one subroutine from another. For example, this was the arrangement like this. Okay, like this we were calling from the main program only. It is possible to call one subroutine from another like this. Let's say if inside the subroutine 1 if we have call sub2, call subroutine 2, if we have like this, then what will happen? From here, control will go to subroutine 2, and then after this return, it will come back to here. Okay. Now, this is called nested subroutines. What actually is going to happen in this particular case? Let's say we are here. Okay, I will just use some other color now. Okay, here. Let's say we are in this main program, we are running here. So from subroutine 1, we go here. Okay, please follow the direction of the arrow. From main program, we are going to sub 1 like this. We will execute sub 1, start executing. Suddenly at sub 1, inside the sub 1, we are getting sub 2. So we will go to sub 2. Okay, like this. Then from sub 2, we will execute the sub 2, and then when it comes, when there is a return instruction, we will come back to here. Then we will continue executing the sub 1, and then we will come back to the original program. Okay, you please note down the flow of instructions or flow of the program pointed by this hand drawn blue arrow. From main program, we are calling sub 1, so control goes to sub 1. Inside sub 1, we are calling sub 2, so if we will go to sub 2, we'll execute sub 2. When this return is here, we will come back to sub 1, because subroutine 2 has been called from subroutine 1 in this case. So that's why this will be the flow. And when we call the subroutine 1 second time, what will happen? From here, we will go like this to subroutine 1. Then we will go to subroutine 2. Okay. Then from subroutine 2, we will come back again to subroutine 1. And then we will return to the original program here. You can see the arrows, the direction of flow of the instructions using the hand drawn arrows in maroon. Now, if you are wondering how automatically it will come back and go to the same locations every time, means why it came back here and not here at the first time, or at the second time why it came back here and not here? It is because whenever there is a call instruction, the full process happens. Full process means which full process I'm talking about? This stack pointer incrementation, copying of the address of next instruction to top of stack, and loading of program counter. This full process happens every time instruction call is executed. So if in this case, when we call subroutine 1, this was x, this was x plus 4. Okay, so because of this call, TOS will become x plus 4, right? This is what we have seen in the first on the previous slide. And because of this call, because after this call we went to sub 1, and after this call we are going to sub 2. So because of this particular call, what will happen? This was m, so this is m plus 4. So what will happen is, when this is running at this time, TOS will be equal to m plus 4, but because before TOS, STKPTR has incremented, right? Stack pointer has incremented by 1. So this TOS means on the stack is like this, first in last out. We keep on writing here, right? We keep on writing one after the other. So when we called the first instruction, when we executed first instruction, x plus 4 was written here, m plus 4 will be written above that, means on the next location. When we are coming back from here, that m plus 4 will automatically be loaded to PC, and here it will come back, and this has decremented. So now TOS will stack to will point to again x plus 4. That's why it will automatically come back to the original location x plus 4. I know this is quite complicated, very complicated thing, but you have to remember the sequence of events all the time. Sequence of events of call is given here. Whenever we are calling, first thing is stack pointer increments, value of the next instruction goes to top of stack, and the address of the label goes to PC. When we are returning, this same thing will happen. But if we are calling another subroutine here, then same thing will happen at that location also. That's why stack pointer will again increment. So if in the original case stack pointer was 0, here stack pointer becomes 1. When we call second subroutine from here, stack pointer becomes STKPTR becomes what? 2. Okay, STKPTR becomes 2, and this m plus 4 is written at 2. See here, 0, 1, 2. And when this return is executed, this m plus 4 will be taken to PC, and this will be decremented, because we have seen during return, the top of stack goes to PC and stack pointer decrements. So top of stack was m plus 4, which goes to PC. That's why this next instruction will be executed, and stack pointer decrements. So top of stack now indicates x plus 4. So at this point, at this return, we'll go back to x plus 4. When this call is executed, it was y and y plus 4. See, when this return was executed, x plus 4 was copied to PC, and this was again decremented. So stack pointer becomes 0. So at this, when this third call instruction is coming in, we'll automatically get top of stack as y plus 4 again. So this is like a whatever you are doing. If you call, then again call, then again call, then it will keep on writing on the stack. Whenever there is a return, it will keep on reading from the stack. So that sequence has to be kept in mind. Let's say if we call it, if we denote this as call 1, this as call 2. Okay. So this will be return 2, this will be return 1. Because first in, last out. Last in, first out. That is what stack is. That is how the stack works, right? First in, this x plus 4 came in first, so it will go out the last. M plus 4 came in the last, so m plus 4 will go out first. This is how stack is going to work. Okay.